Okay, hello everyone, and welcome to the AMS Mountain Meteorology webinar series. I'm gonna just keep talking here as I see a lot more people joining as we're going here, but we want to get started in the interests of time, so Tina has plenty of time for her talk. I'm Ethan Gutman at the National Center for Atmospheric Research, and I'm pleased today to be presenting Tina Chow from UC Berkeley to be telling us a bit about crossing multiple gray zones in atmospheric modeling, turbulence, convection, and topography. I do want to point out that if you learned about this webinar series from something other than my normal emails to the mountain meteorology community, please feel free to send me an email and get in touch, and I can add you to the mountain meteorology webinar list. My email is gutman@ucar.edu. You know what, I should probably just put that on the slide here. Feel free to reach out if you have any technical difficulties, or if you want information about upcoming webinars. You can also find us on the Mountain Meteorology webinar website, which you can find just by Googling AMS Mountain Meteorology webinar. I'm excited to hear today's talks. This is something that becomes more and more of an issue as we get higher resolution atmospheric models. Even our operational forecasting models like the HRRR are getting down into this gray zone. So I will pass this off to Tina in a minute here, and you should all be muted. We will try to go for about 45 minutes or so of talk, and then have an opportunity to raise questions or ask questions at the end. If something does come up in the middle you urgently need an answer to, feel free to type something into the chat, and we can see if we need to get it answered as we're going. So Tina, if you are ready, I'm going to stop sharing so you can take over. Take it away.
Okay, can everyone hear me?
I can, and hopefully nobody else has unmuted.
Okay. All right. All right, and is the slide showing correctly?
Looks good.
All right. Well, hi everybody. I'm really excited to be here today to tell you about some of the work we've been doing about crossing multiple gray zones in atmospheric modeling. And I'm going to touch on several different examples, several different areas, covering turbulence, convection, and topography, some examples in more detail than others. And the work that I'm going to be showing today has been done by several current and former postdocs and students: Bobby Arthur, Katie Lundquist, Xiaoming Shi, Jason Simon, David Wiersma, and Bowen Zhou. And we've also done this in collaboration with some others, and I'd specifically like to highlight Bob Street and George Bryan, who worked with us on the cloud simulations that you'll see, and also Nicolina Bahn, Christoph Scher, and Linda Schlemmer at ETH Zurich, who worked with us on a review paper that came out this year in Atmosphere on this exact topic, crossing multiple gray zones. And you will find more details in there. I've covered a few of the examples in the seminar, but not all of them. But the themes that I'm going to talk about are in that review paper. So whenever I think of the gray zone, an image never fails to come to my mind of just a gray image picture. But of course, that's not what we're talking about. It's a different kind of grayscale, what we mean in the gray zone. And it's a little bit maybe more like this, where it's pixelated and you're losing some information, and it's a little unclear what we need to do. So I'm going to talk about what the gray zone is and how we approach it as we cross different resolution scales in atmospheric modeling. So to motivate that idea, I'll just start with an example of a flow where we might be interested in transitioning from the mesoscale to the microscale, and this is for an urban flow. So at the mesoscale, you might look at this whole urban boundary layer and parameterize it with some kind of urban canopy model, and you might have resolutions on the order of 10 kilometers or maybe 50 kilometers. But there may be some reason that you want to know something about what's happening on the neighborhood scale. And so if you zoom into a local scale, you might say, well, I'm going to have a different kind of roughness length in this part of the city than I am in the downtown area, which has taller buildings. And so you have more local influence. The buildings are still probably parameterized, but you might have internal boundary layers that develop in different parts of the city at sort of intermediate resolutions. And then you might zoom in even further to the microscale, where you're looking at individual buildings and flow around each individual building, looking at eddies in the lee of the buildings, and really very fine resolution, maybe 1 or 2 kilometer resolution. But all of those scales are connected And the influence of the mesoscale and the microscale is important to include. And the way that that's done typically is through grid nesting in atmospheric modeling. So we'll talk about how that works and what happens as we transition through these scales. So that's just one example of a microscale flow that might be interesting. We are interested in microscale flows for understanding microclimates, fog and marine layer flows and weather prediction. In urban air quality and urban dispersion, we might want to know what's happening in urban environments in detail in particular neighborhoods, which are closer to certain pollution sources. Over complex terrain, steep mountains might affect, and topography in general affect siting of wind turbines and also prediction of fire weather. So there are lots of different microscale flows that we're interested in being able to simulate while also considering the mesoscale influence on them. So in mesoscale modeling, we've traditionally had sort of a synoptic scale model, the very, very large global scales. And at the very fine scales, we have large eddy simulation, which traditionally was used in a very idealized way. And somewhere in between, we have mesoscale simulation. So the length scales range from greater than 2,000 kilometers to down to 2-meter resolution that we use in LES to capture scales that are less than a kilometer or two. So what I'm going to be talking about today is the transition from the mesoscale to the LES. And the question that comes up is, what happens in between what is traditionally done at the mesoscale? Say you might have 10-kilometer resolution and what's traditionally done at the LES with say 100-meter resolution. And that is called the gray zone, or sometimes the terra incognita, which was a phrase introduced by Wingard to describe this problem and the challenges in representing turbulence in these intermediate scales. So the question might be, do you push mesoscale models to higher resolution and push these mesoscale models that were designed to work at the mesoscale down to finer resolutions? Or do we say, let's use LES models and just make the domain size bigger? What happens? What happens in the gray zone? Is there some kind of conflict in the mesoscale approach versus the LES approach? And how do we figure out what that is? So to describe the gray zone, I think it's really helpful to think of a feature of interest that you might be interested in simulating. Maybe it's gap flow in a particular mountain range, or the wake of some structure that you're interested in, or maybe it's a cloud or the boundary layer depth. So we'll just use a cloud here as an example of an atmospheric phenomenon that we're interested in representing. And this cloud, say, has a length scale of 1 kilometer. So how does this cloud get represented in a model? It depends on what the grid resolution is. At the largest scales, a general circulation model at GCM might use a resolution of 100 kilometers, and then you would have a very large sample size, and you would treat an ensemble or an average of these clouds and parameterize the effect of the clouds using some kind of convective parameterization. So in this case, the resolution of the model, the grid spacing delta, is much larger than the scale that you're interested in. And so that those clouds are completely parameterized. On the other end of this, in large eddy simulation, or sometimes in very fine cloud resolving models, you have grid spacing on the order of 100 meters, and you're able to explicitly resolve the features in the cloud and the convective motions and everything that's going on in there. And you don't have to parameterize things because you're resolving the most important scales in this flow. So in this case, the grid spacing in the model is much less than the length scale of the feature of interest. So in this case, much less than 1 kilometer. So in between, in the gray zone, you have sort of intermediate resolution. Maybe your resolution is 1 kilometer. And in that case, the resolution of your grid is about the same as the length scale that you're interested in. So you have very, very poor representation of the cloud in this case. Maybe you have a couple grid points across the cloud, and you're not able to fully resolve everything that's going on. But on the other hand, the parameterization, say a convective parameterization, would be inappropriate because you are resolving some finer scale features, and the parameterization developed for, say, 100 kilometer resolution wouldn't be valid here when you have 1 kilometer resolution. So that's an example of the gray zone, and you can apply that concept to other features of interest that you might be interested in, and that will depend on what flow you're looking at. And we encounter many of these different gray zones as we cross into different resolutions in atmospheric modeling. So numerical weather prediction now might be at 10-kilometer spacing, the NAM or the ECMWF model, but we're quickly advancing to about 1 kilometer spacing, and it's already being run by Meteorology Swiss at 1 kilometer resolution. They're running Cosmo, and the NOAA-HER model is at 3 kilometers, and there's certainly much finer versions of all of these being run experimentally. And so the way these are set up at these finer resolutions involves some kind of dynamical downscaling or grid nesting. And people are pushing this even further down to the LES scale. So at the mesoscale, maybe you start at 12 kilometers and you're refined by some kind of multiples until you end up at, say, 50 meters for a large eddy simulation. Well, somewhere in between there, you're crossing through what we call the gray zone, where we're not really sure, should we apply a mesoscale closure or a simulation approach at 1 kilometer or at 450 meters or even at 150 meters? Is that really an LES, or is that a mesoscale closure that you should use, mesoscale approach? So those are all the questions, or the beginning of some of the questions. And just to give you an example of people pushing models down to finer resolution, there was a paper recently in Nature that was talking about regional climate change and how they saw heavier summer downpours at higher resolutions under climate change conditions. And in their simulations, in their setup, they used 1.5 kilometer resolution. They turned off the convection scheme, and they used a Smagorinsky turbulence closure model. And so they're drawing conclusions from a simulation that's done at gray zone resolutions, arguably. So the question is, how can we trust the results in these intermediate gray zones when we're using models that were designed at the mesoscale? And maybe in this case, using closure models like a Smagorinsky type approach that maybe was more of an LES closure. What's happening at this intermediate scale? That's what we're trying to get a better handle on, because we are pushing into those scales as we move to higher and higher resolution. So turbulence modeling is one of the challenges in the gray zone. Questions also about other physics parameterizations. When do you turn them off? When do you turn them on, like convective parameterizations? Similar questions about land surface and topography. And so I'm going to try to address some of these. What we're doing in the gray zone is to try to build a model that can work across all scales. We're primarily using the weather research and forecasting model, WRF, to transition from the mesoscale to the microscale. I have results from a couple other models we're using as test models and in the examples in this talk. And the first thing I'm going to describe is sort of a performance analysis. How well does WRF do in the gray zone, or how well do these mesoscale models do in the gray zone, or LES equivalently, whichever example we're looking at. So some of it's just going to be like, can we quantify what's going on there? Is it doing a good job or not? And ultimately, our goal is to develop a model that will work for all scales. And the approach that we're taking to do this is to improve the turbulence closures that are used, drawing from large eddy simulation and applying those across the gray zone. And then in terms of topography, looking at the immersed boundary method at certain resolutions. So there's a lot of open questions in the gray zone. You might want to know, how do the space and timescales of the turbulence that resolve change as you transition across resolutions, say at 100 meters to 10 kilometers? How do you even know if you're in the gray zone? You set up your simulation and it's looking okay, but how do you know? How should we set up a grid? How should we use nesting to optimally represent turbulent mixing at all of the different grid scales that you're running at? And finally, what is the role of the closure model, the turbulence closure model, on representing these features when they're partially resolved? So I'm going to go through a few examples of different gray zones. The first one I'll spend a lot of time on is the convective boundary layer. And then I'll show you examples with a stratocumulus cap boundary layer, a quick example of deep convection, and at the end, talk about topography. And the first three are going to be connected in some way by talking about the turbulence closure model. And the approach that we're taking there is to compare different models, including one called an explicit filtering and reconstruction approach. So you'll hear more about that as we go on. So the first example with the convective boundary layer is really just to look at how the model performs, or how a mesoscale model performs as you move into the gray zone, as you go to finer and finer resolution. So this convective boundary layer situation is just a warm, sunny day. The sun is heating the ground, and you have thermal plumes that develop, and you get convection, and maybe there's clouds, but not in this case that I'm showing you. It's just a dry convective boundary layer just to start with. But if you took a slice, a horizontal slice across here, you would see these updrafts and downdrafts. And if you look at vertical velocity at 150 meters above the ground, you see updrafts in red and downdrafts in blue. And you see this organized structure where you have these convective cells that have formed. And this simulation is at 25 meters, and it's very well resolved at this resolution. You can zoom in to where that box is, and you can see more clearly that you have these narrow updrafts in red and these compensating downdrafts in blue at this particular height above the ground. So this kind of resolved structure is very similar to what you see at very small scales, Rayleigh-Bernard convection. This is in a small dish. You're looking down and you have heating at the bottom plate, and you start to develop these organized motions. And some of the theory that applies to Rayleigh-Bernard convection can be applied to the atmospheric boundary layer. And it helps you to determine when there's going to be convection and when there isn't. And that's in terms of the way the model is seeing convection, not whether it's happening in reality or not. So the convection that you see in the model is actually quite resolution dependent. So if you're running the model at large eddy simulation scales with a grid spacing much less than the length scale of interest, convection can occur naturally. It's sort of independent of grid resolution. So in this case, if you run this convective boundary layer at 25-meter resolution or at 50-meter resolution, you're going to get very good agreement in the results independent of that choice of resolution, and you'll see convection occurring naturally. At the other end, if you run this at very coarse resolution, say at 5-kilometer resolution, you cannot have explicit convection in the model because what we call the grid-dependent Rayleigh number is too large, and all of the mixing ends up being done by the subgrid scale turbulence, the PBL scheme that you choose, whatever that closure scheme is. But in the gray zone, you can have convection depending on what the grid-dependent Rayleigh number is. And that Rayleigh number that will allow convection to occur is reachable, but it depends on the grid and the structure of the cells that are created. That structure is also grid dependent. And so I'll show you some examples of what that looks like. So what we did to test this was to set up the classic Wangara experiment day. It's just a prescribed heat flux at the ground, a sinusoidal heat flux, prescribed lateral forcing, clear boundary layer. And it's a very well-studied case. And we looked at this case with different resolutions. So at the mesoscale running at 3.6 kilometer resolution, at the LES scale going down to 25 meters or 50 meters, and in between looking at some gray zone resolutions. So the closure model at the LES level was a TK 1.5 closure. At the mesoscale, it's the Sun and Chang closure. It's a PBL scheme. And the 25-meter simulation here is considered our truth. And then we have the mesoscale at 3.6, and I'll show you examples from a gray zone simulation at 1.2 kilometers. So this case proceeds with heating at the ground that increases in the morning hours. And you can see the potential temperature plotted here showing the depth of the boundary layer growing at 12 noon versus 15 and 18 Z like later in the afternoon. And in overall structure, we see that the LES and the mesoscale and the gray zone model capture the overall development of the boundary layer. In the LES case, the convection is actually resolved, but in the mesoscale case, it's all subgrid scale. And so in a heat transfer sense, you can think of it as conduction. It's just a very high diffusivity. But overall, the bulk statistics or the mean properties here are pretty well represented. If we look into more detail though, we see that the structure of the convective boundary layer is very different. So here again is what we expect to see at 25-meter resolution with these updrafts and downdrafts. And if I show you what happens at the 1.2 kilometer run, you also see these kinds of features where you have updrafts in red and downdrafts in blue, and a very organized structure again, right? They look like these convective cells, kind of like what we see on the 25-meter grid. But if we compare these at the same size, like the same domain size, this is the 1.2 kilometer on the left and the 25-meter on the right. And you notice that the size here of this cell is 8 times the boundary layer depth, whereas in the 25-meter run, it's only about 1 times the boundary layer depth. So we see grid-dependent structures that are developing here that have to do with what resolution we're using and not what the true convective state is of this particular case. So one way we tried to compare that is to say, okay, well, if we have this 25-meter run, what would it look like if we filtered it to 1.2 kilometer? If we have this true LES, very fine resolution, what should it be looking like if we were running a 1.2 kilometer grid? So what we did is we took the 25-meter resolution simulation and we applied a Fourier cutoff filter to remove scales that were coarser than 1.2 kilometers, and you transform that back, and this is what that looks like. So this is the filtered 25-meter results at 1.2 kilometer resolution. So you can see the structures are very different. We don't have the same organized cell pattern. Instead, there's more variability. And you can see that better by comparing the 1.2 kilometer straight results on the left and the filtered 25-meter results. So this is what we had, the 25-meter filtered to 25 meters, filtered to 1.2 kilometers from the 25 meters. So side by side, you see very, very different kinds of structures. And these structures are able to be resolved in the 1.2 kilometer grid. They're just not forming naturally on the 1.2 kilometer grid. And that has to do with the closure model and how the convection is represented either explicitly or using the subgrid closure. And we'll show some more examples of that in a bit. One other interesting thing that happens is that the timing of the onset of convection very much depends on the resolution that's chosen. So we're looking at here at the total UU variance as a function of time. And you can see that as the heating begins in the morning, that this increases and it plateaus to some level in the mesoscale model. And the LES actually agrees very well with this. And that's because in the LES, you're explicitly resolving the convection. In the mesoscale, you're fully parametrizing it. But in the gray zone, in these bumps here that you see this onset of convection happening at different times. So at 800 meter resolution, it's happening at say 12 o'clock. At 2000 meter resolution, it's happening a few hours later. And basically what you're seeing here is the effect of that grid dependent Rayleigh number. And it takes longer, it takes more heating for there to be enough heat at the surface in order to trigger resolved convection at the gray scales compared to at the LES. The mesoscale will not convect at all. So this is an interesting thing to think about in, as we transition into these gray zone scales, is that the onset of the convection is dependent. We're going to look at how that varies with the closure model in a bit. Another thing that is important to think about is that when you have this kind of grid dependent convection and you use grid nesting, that the grid dependent structures can propagate into the finer grid. So on the left here, you see a standalone simulation at 400 meter resolution, and you see these convective cells that have developed in this gray zone simulation. And on the right, this is a 400 meter resolution simulation that was nested inside a 1.2 kilometer grid. And the flow in this case is coming from the southeast down here. And so as the flow comes in, you can see that there's much larger scale structures that are coming in from the 1.2 kilometer grid. And it takes quite some time for the smaller scales to develop at the 400 meter resolution. So the idea here is that when you're using nesting, that the larger scale features, and they may not be actual real features, they're features that are grid dependent, those are being translated and input into that finer domain. So what do we do about this? Well, for this convective boundary layer case, you might ask, well, should we allow convection or should we not allow convection? If you do have convection, we see that it ends up being grid dependent. The cell structures that develop depend on what delta X you've chosen, whether it's 800 meters or 400 meters or whatever. And the timing of that onset of convection also depends on the resolution that you've chosen. On the other hand, you could choose to not convect and pretend that you're running a mesoscale model by increasing the eddy diffusivity and damping all of those scales out, but that would end up being a pretty expensive mesoscale grid, mesoscale solution, because you wouldn't be taking advantage of the finer resolution that you have. So a couple ideas that we've looked at. I'll just mention the first one really briefly, which is triggering smaller scales sort of manually as you go to the finer grid, or looking at the effect of the turbulence closure model. So just really quickly, I'm not going to talk about this much, but in other work we've been exploring, and several others have also been exploring using the cell perturbation method. And what you see here is a case with a stronger forcing. This is not just convective boundary layer, but you see these large scale structures that develop at the inflow from the outer grid, these streaks that develop. And towards the end of the domain, you see them break up into smaller scale features. The cell perturbation method, developed by Esparza and others, puts perturbations at the inflow boundaries. And you can see that finer scale structures and turbulent structures develop much sooner when using this kind of artificial triggering of turbulence near the boundaries. So I'm not going to talk about that more here, but that is something to explore, to think about how to generate the correct scales as you nest from mesoscale to the microscale. What I am going to spend some more time talking about is the effect of the turbulence closure model. And specifically, we're going to consider a scale-aware closure model that uses the length scale of the grid resolution as the basis for the turbulence closure instead of using a PBL scheme at the intermediate resolutions. And the question is whether this will help with crossing into the gray zone. So the approach that we've developed and tested at many different resolutions is called the dynamic reconstruction model. And this is an explicit filtering and reconstruction approach. And I'm not going to go into the details here, but if you're interested, I'm happy to explain the method to you. The basic idea is that you apply two different operators to the Navier-Stokes equations. In large eddy simulation, you apply a smooth filter to separate large scales from smaller scales, but we also have a discretization operator. And so if you separately consider a filter that's applied to the Navier-Stokes equations to generate the LES equations and keep that separate from the grid resolution, then there are some scales that can exist between the filter scale and the grid scale. And by taking this into account, you can actually limit some discretization errors and also expand using series expansions to recover some of the scales between the grid filter and the LES filter. And that's using something called an approximate deconvolution method. So that probably doesn't tell you anything unless you've already heard of this, but you can look for more details in the papers. And what you end up with is something called a mixed model. I'll just show this part down here. It's a scale similarity model that has this piece that's combined with an eddy viscosity model. And so this approach we call the dynamic reconstruction model. The eddy viscosity coefficient is actually determined dynamically. It evolves in space and time as the simulation continues. So the key idea here, and to try to summarize why this approach is different than just a standard eddy viscosity approach, is that we have the turbulent stress divided into a resolved subfilter scale portion that you can actually reconstruct, plus a subgrid scale. And traditional models don't include that reconstruction piece. And so an eddy viscosity model just has the SGS component, and it assumes there's an equilibrium state, and it's entirely dissipative and sometimes overly dissipative. There's no backscatter allowed from small scales to large scales, and it usually assumes that the turbulence is isotropic. In contrast, dynamic reconstruction models include that resolved subfilter scale piece, resolvable subfilter scale piece. And we do this by explicit filtering to separate the scales, and then using a mixed model and a dynamic piece to a mixed model that reconstructs this part. This ends up giving you an anisotropic formulation. It allows backscatter of energy from small scales to large scales, and it overall reduces truncation errors from the numerical scheme because it separates the scales in this way. So I'm going to show you some examples of how we applied the DRM to this convective boundary layer case, or a similar case that I just described earlier. And our idea here is to see whether the turbulence closure model affects the development of these structures in the gray zone, in the convective boundary layer. So here's some simulations using the Smagorinsky model. And what you're looking at here are different profiles at different times of the day after the start of the simulation. So 0 hours up to 9 hours. And you see the convective boundary layer developing. This is potential temperature versus height. And the black dashed lines are the benchmark simulation at 25-meter resolution. So that's like the large eddy simulation. You can see the PBL growing as time goes on. And the colored lines are the results using the Smagorinsky model at 1 kilometer resolution. So you can see some errors in the prediction here and a really big delay in the development of the the mixed layer here. On the right is the same thing with just a different Smagorinsky coefficient, just to see if we could sort of tweak the model and get it to behave better, but not really. We see a very different result when we use the TKE 1.5 closure, and these results are in WRF, I should mention. These are just with the standard configurations in WRF. With the TKE 1.5 closure, you see much better agreement with the benchmark 25-meter simulation, maybe some disagreements in the slope of the mixed layer and near the surface here, and again on the right is just with a different coefficient in the TKE closure. And then here are the results with the dynamic reconstruction model with zero-level reconstruction. And we have nice mixed profiles from the beginning. At higher reconstruction, which is the panel on the right, there's a little bit of an oscillation near the surface that I think has to do with the surface layer representation in this particular application. So let's look a little bit at the onset of convection using different closure models. So this plot is a time series of the W prime theta prime as a function of time. And at 25-meter resolution, that dashed black line, you see this increase very near the near the beginning of the simulation, which indicates the onset of resolved convection. And contrast that with the green solid line here, which shows the results at 1 kilometer resolution. And you see a 3-hour delay in the onset of convection here and sort of intermediate levels at the intermediate resolutions. So that's with Smagorinsky. And then you can see with the TK 1.5 closure, the onset looks very different. The delay at 1 kilometer resolution, which is the solid green here, is 3 hours less than what we saw in the Smagorinsky model. And that was also reflected in the potential temperature profiles that we saw earlier. With the dynamic reconstruction model, we see even less of a delay of the onset of the convection. So this just shows that choosing the different closure model affects the development of these organized cells and the timing of the onset of these cells in the boundary layer. So now let's look a little bit about what the structure of those cells is using the different closure models. So here's a snapshot similar to what I showed you before, just showing the W velocities at 25-meter resolution. So this is our true LES result. And now look at the convective cells as we cross into the gray zone using two different closure models. So on the top row, we have the TKE closure, and on the bottom, we have the DRM. I didn't show the Smagorinsky closure here. The structures there are much, much bigger. So on the left, we have 100-meter resolution, and at 100-meter resolution, TKE 1.5 and DRM look pretty similar in terms of the size of the structures. They look even closer at 25-meter resolution. And then we progress as we move to the right to coarser and coarser resolution, 200 meters, 500 meters, and 1 kilometer. And you can see the size of the structures that TKE produces are the size is much bigger in the top panels compared to what you get with the dynamic reconstruction model. So from this, you can of course compare to what you really want. At the 25 meters, you can look at the filtered 25-meter results like we did earlier to show what kind of scales should develop. And the DRM is closer to maintaining the fine scale structures that that filtered 25-meter grid would show. So one way to quantify this, you can see it pretty easily visually by just looking at the patterns here. But one way to quantify the difference is to extract a critical length scale from this. And the way we do that is using an energy spectrum and finding not the peak wave number, but 2/3 of the energy wave number. There's a particular way to get it. And looking at that critical wavelength as a function of resolution for the different closures. And so that's what's plotted here. Lambda C is the critical wavelength. And here we have resolution on this axis. And you can see different closure models. And so this is showing here at 0.1 kilometers, so at 100-meter resolution, the critical length scale, which is basically what you're visually seeing as the size of those convective cells, is pretty constant from 25 meters to 50 meters to 100. But then as we go to coarser resolution from there, we see a big difference in the results depending on the closure model. And Smagorinsky is the one that deviates the most. The size of those cells becomes really, really large as we approach 1 kilometer resolution over here. And you can see that the DRM with 0 level and 2 levels of reconstruction here stays the flattest, meaning that it's able to maintain the closest length scales to what we originally saw at the 25-meter grid. And the TKE model is showing slightly larger structures at 1 kilometer than the DRM, and that's what we saw in this previous plot over here. So this is one way that we've tried to quantify the scales and the size of these structures in the gray zone, and to use this to try to determine whether we're even in the gray zone. We see here that for this particular CBL, we're transitioning into the gray zone at about 200-meter resolution. That's when the models are no longer giving the same length scales as what we had at the finer resolution. And we also see that this transition depends a lot on what closure model that we've chosen. So I'm going to show you a couple other examples of how we've explored using the closure model and explicit filtering and reconstruction in the gray zone to see the impact. And the first one is a stratocumulus capped boundary layer. So there's a lot of question and uncertainty about representing clouds in global models. And as these global models start running at finer and finer resolution, we wonder if that's going to fix the problem. So if you look at this, this image off the coast of California showing all of these stratocumulus clouds, if you run this model, run a global simulation at 1 kilometer resolution, sometimes what you see happening is that you, instead of having closed cell convection, you end up with open cells, and the cloud fraction, the cloud coverage is much less than what would be expected. So increasing the resolution doesn't necessarily fix this problem. And when stratocumulus clouds are covering, say, 20% of the globe, this can be a very significant error that would occur if these models are just pushed to finer resolution without thinking about whether the structures and the features represented are correct in this sort of gray zone at 1 kilometer. So we're looking at how to accurately represent this stratocumulus capped boundary layer and how that depends on the resolution and the closure model chosen. So we looked at the test case from the DICOMS-2 experiment that was described in the Stevens et al. Paper in 2005. And for these simulations, we're using NCAR's CM1, Cloud Model 1. And it's an idealized setup, and it's trying to reproduce conditions that were observed in the field. And this Stevens et al. Paper describes 16 different LES models, and they're using resolution as fine as 5 meters in the vertical. And even then, many of the models are under predicting, they're not able to predict the correct cloud water. So this is a time series plot here from 0 to 4 hours showing vertically integrated cloud water. The observations showed that the clouds were really steady, this blue line here. So the cloud water should have stayed about steady over this 4-hour period. And this black line here shows the mean of this ensemble of LES models, and the shading here shows the range of different model results. So what this paper basically, well, one of the conclusions was that even at 5 meters, there's a lot of sensitivity to what's happening at the cloud top, and many of the models underpredict this cloud water. So we used this test case and looked first at fine resolutions to see the difference in the different closure models, to see the sensitivity of the model setup. So this is the liquid water path time series as a function of time over 4 hours again. And on the left, you have the simulations with the TKA closure, and on the right, it's with the DRM closure. And looking at different vertical resolutions. So with DZ equals 5 meters, that's the red line here. You see the TKE model tracks around the mean of the Stevens et al. Paper. And the DRM actually produces more cloud water, which is closer to what the observations predicted, which was pretty constant across this 4 hours. And these are at different vertical resolutions. And you can see overall, the DRM is able to predict more cloud water compared to the TKE model at coarser resolutions. So at this sort of standard resolution that was set up in the Stevens et al. Paper, we have the DRM showing more cloud water. This is the closed cells of the stratocumulus that you would expect to see. With the Smagorinsky model, you have a lot of dark, non-cloudy areas. With the DRM, it's mostly completely cloudy in the simulation. So the DRM is showing that even at the standard resolutions, you're better able to maintain the cloud water. So here's a vertical profile through the cloud with TKE on the left, DRM on the right again. And so this is cloud water mixing ratio as a function of height. The initial conditions in the simulation are the dashed black line, and the circles here are the observations. So again, this is showing different resolutions. The TKA closure isn't able to maintain all of the cloud water. And so you see it's really under predicting compared to the observations here. And the DRM, on the other hand, does a pretty good job at 5 and 10 meter resolution compared to what you saw in the TKE closure at maintaining this cloud water. At coarser resolution, it underpredicts again because it entrains too much at the top of the boundary layer. So you can also look at higher order statistics. This is the variance of the vertical velocity, again, for TKE on the left and DRM on the right. The solid circles are the observations and different model resolutions again. The DRM does a much better job of capturing the variance of the vertical velocity, particularly at the finest resolutions. And then we looked at different levels of reconstruction in the DRM and different variations. I won't go into the details here, but with 0 order reconstruction compared to 5th order reconstruction, you can see the DRM is much better able to capture this velocity variance again. And this is at the same colors, this is at the finest resolutions. But on the right, this panel is with 5th order reconstruction compared to 0 on the left. Okay, so next we said, let's take a look at what happens in the gray zone. So all of these simulations were sort of the standard resolution. We were looking at different resolutions in the vertical and different closures, but now what happens in the gray zone? So this is a simulation with a fairly coarse or intermediate DZ of 25 meters and a delta X of 1 kilometer. And you can see the DRM here is just a snapshot showing a lot of cloud cover. So it's able to maintain that cloud cover compared to the Smagorinsky model where you see a lot darker colors and much less liquid water. So here's a time series again of liquid water path for the TKE, Smagorinsky, and DRM closures. And just if you step back and look at this, you automatically see the DRM is able to maintain much more cloud water compared to either of the two eddy diffusivity closures. And these are different horizontal resolutions seen here. So even at 1 kilometer resolution, which is the black lines here, and Smagorinsky had a lot of trouble with the 1 kilometer resolution. Even at 1 kilometer resolution, of course, none of the models are perfect at 1 kilometer, but the DRM is able to maintain much more cloud water at that resolution. One of the reasons why we think the DRM is able to do a better job at these resolutions and even at the finer scales is because the DRM allows for backscatter of energy. And this is a PDF plot showing the transfer of energy, technically the transfer of variance of potential temperature. And the positive numbers here, greater than 0, indicate dissipation. And the left side, the negative numbers, indicate backscatter. And the Smagorinsky in blue and the TKE in magenta here are only on the positive side. They don't have, like the blue and magenta here do not extend to the negative because they do not allow any backscatter, as compared to the DRM and the red one is just a simplified mixed model. All of those do allow backscatter, and we've compared with observations in previous studies, but this is one of the features that's kind of unique to the DRM in that it allows backscatter from small scales to large scales and may help introduce small scale variability that helps with the second order statistics and the structure of the result features that we see in the flow. One other quick side point that we discovered in this is that there's a lot of sensitivity to the choice of the Prandtl number, and the Prandtl number is what relates the diffusivity for scalars to the diffusivity for momentum. So in a traditional WRF setup or in a traditional closure model or just mesoscale model, there'll be a constant Prandtl number that's chosen, typically between 0.3 and 1. People use different values. But using the DRM, we can actually dynamically calculate an eddy diffusivity without using a Prandtl number. And we found that the eddy diffusivity that is calculated dynamically results in a Prandtl number that actually ranges from 0.5 to 10, depending on what layer in the boundary layer you are at, which is very, very different than the constant Prandtl number solution. So if you look here at this profile of liquid water, the model, the observations again are in black. And if you use a dynamic eddy diffusivity, that's the blue line here, you are able to maintain much more cloud water compared to using a Prandtl number, a constant Prandtl number determined eddy diffusivity. So this is kind of a side point, but it turned out to be a very important one for these simulations, that we found that scalar and momentum, scalar mixing and momentum mixing should be treated separately, meaning don't use a constant Prandtl number. Instead, dynamically calculate what Km is and what Kq is, what the eddy diffusivity is for scalars. All right, So we were encouraged by the performance of the DRM at these resolutions for these examples that I've showed so far for the convective boundary layer and the stratocumulus cap boundary layer. So really quickly, I'm going to show you results, not in much detail though, of a deep convection case that we tried to examine at gray zones as well. So the deep convection case that we simulated is from the Gate 3 field experiment, and we followed the setup of Karutanov et al. And the benchmark simulations are with a horizontal resolution of 100 meters, vertical resolution of 50 to 100 meters. And then we looked at gray zone simulations where we coarsened the grid to 1 kilometer in the horizontal and 100 to 500 meters in the vertical. So just a quick snapshot of results. This is from the benchmark simulations showing cloud fraction as a function of height. And you can see that all of the closure models, the DRM, different variations of the DRM and the TKE and the Smagorinsky model all agree at this resolution, at 100-meter resolution, meaning that the dominant scales and features of this flow are well captured. And in the background in the gray is results from the previous study. So at fine resolution, all of these cloud fraction profiles converge. But in the gray zone, we found that the convection, the deep convection that is simulated strongly depends on the closure model. So this is at 1 kilometer resolution. The benchmark is in the black dashed line in the envelope of simulations in the gray. And we can see that the DRM in magenta here is much better at predicting the cloud fraction as a function of height compared to the TKE closure model. So this is described in much more detail in the paper. But one takeaway is that backscatter seems to be very important in driving this convection at this intermediate or gray zone resolution of 1 kilometer. And here's just an image from the simulation at the very finest resolution showing the deep convective simulation structures. Okay, so more details about that case in that paper down here if you're interested. So finally, I'd like to talk about topography and how topography has its own gray zone. So what happens as we go to finer and finer resolution? If we look at a mountain at 3 kilometer resolution, the grid doesn't really see all of the steep slopes, and maybe the max slope that you see is 4 degrees. But as you go to 1 kilometer resolution or 300 meters or 100 meters, the max slope that's resolved increases dramatically to say 32 degrees in this case, or much finer sometimes. So the problem is that most mesoscale models use a terrain following coordinate system where the coordinate is stretched over the surface of the topography. And as the terrain becomes steeper and steeper, you end up having truncation errors from the horizontal gradients, such as the pressure gradient. And these problems start at about 30 degrees, and either your simulation will become unstable and blow up, or you'll have large truncation errors and other things may happen. And there's some guidance about what kind of grid aspect ratios to choose. But in general, very fine scales, there's not a good way to represent steep topography using terrain following coordinates. So we've developed what's called an immersed boundary method, IBM, that's been used for decades in various engineering flows. We've developed an IBM approach that goes into WRF. And in the top, what you see is Granite Mountain in Utah represented with a terrain following coordinate. On the bottom, you see this same mountain with the immersed boundary method. And you see there's a background Cartesian grid, and the topography is overlaid or embedded, immersed in that background Cartesian grid. So the way this works is to look at the cut cells, the cells that intersect with this immersed boundary, and you find ways to apply boundary conditions near that near the cut cells. So this is one example that's shown here using ghost cells, and there's other ways using velocity reconstruction that we've been testing in WRF. And this allows WRF to handle very highly complex topography. And so even if the terrain slope approaches 90 degrees, like for buildings, you can represent this using the immersed boundary method. So some of the things we've been developing are ways to do hybrid grids where you use terrain following coordinates for part of it for representing the topography, and then you might immerse the buildings on top of this. and also the ability to do nesting from mesoscale down to a fine scale simulation that uses IBM. So I just have a couple of examples of the immersed boundary method in WRF. The first one is a complex terrain example just to illustrate the capabilities of WRF IBM. And so this is a simulation of a downslope flow at 25-meter resolution. And what you're looking at is isosurfaces of downslope velocity. So this is at sunset, and you see a drainage flow that develops in the valleys, in these side valleys on the mountain. This is Granite Mountain. And this simulation at 25-meter resolution has very, very steep slopes. And this is not something that we can run using terrain following coordinates. So this is just an illustration of what we can do at the very finest scales using the WRF IBM setup. So what we've been working on for a long time is to make multi-scale simulations possible with WRF IBM. And the idea is, just like we had at the beginning, this image of a nested setup where you're going from the mesoscale down to the microscale. This is for flow around Oklahoma City. And the finest grid here is 2-meter resolution. So there's an immersed boundary method being used at this finest resolution, and it's being fed by the larger scale simulations on the coarser grids. And this process required a lot of work to get the different coordinate systems to talk to each other appropriately. But we're now able to look at simulations of, say, a scalar release in a downtown area that is very highly resolved locally at 2-meter resolution, but is also influenced by the mesoscale forcing and the mesoscale variability and meandering in the flow that is coming in from the lateral boundaries, just in a standard nested setup that you would have in WRF, but able to resolve topography at much, much minor scales. So the question now is, what do you do with buildings at different resolutions? At 1-meter resolution, we're able to resolve them quite well, but at 1-kilometer resolution, you wouldn't even try to use an immersed boundary method for buildings. Instead, you would use an urban canopy model. So the question is, what about the gray zone for topography, where the length scales of interest are similar to your grid resolution? And the same thing happens for buildings. This little image here shows buildings represented at different resolutions from 10 meters to 1 meter. So when it's looking nice and crisp here, let's see, like right here, that's 1-meter resolution, and then you coarsen the grid and the buildings are not super well represented, and you're in the gray zone for the building representation. So that's an open question about how do we transition from a terrain following system or a canopy, urban canopy representation to something where you're explicitly resolving the topography and the buildings if needed. Okay, so I hope that some of this has shed some light on the gray zone. I've showed you some examples of convective boundary layers, simulations to kind of assess how do we know when we're in the gray zone, how well do the models do in the gray zone. We showed some examples of the stratocumulus capped boundary layer, a brief example of deep convection, and then talked about topography and the gray zone that it encounters. One common theme is that the turbulence closure models do really matter. We've addressed some of the questions that I posed in the beginning about how do the turbulence structures evolve in space and time at these intermediate resolutions? So at 500-meter resolution, and how does the closure model affect that? How do we even know if we're in the gray zone? Well, this critical length scale can be used as one metric to look at the structure of the resolved cells that are produced by the model. How might you optimize grid nesting? Well, the cell perturbation method is one thing to think about as you try to nest to finer and finer scales. And how does the turbulence closure model affect partially resolved flow features? We saw in this deep convection case, for example, that it made a dramatic difference in the representation of cloud fraction. So one key takeaway that I hope you come away with is that there are multiple gray zones that exist depending on what you're looking at, depending on what your resolution is and what your scale of interest is. And the gray zone is roughly defined by when your length scale of interest is approximately the same as your grid resolution. So that grid resolution is going to be different depending on what flow feature you're looking at. So in the convective boundary layer, you might run into the gray zone at, say, 200 meters. In the stratocumulus capped boundary layer, it might be more like 50 meters or 25 meters. Like in the stable boundary layer, you might even be in the gray zone at 10 meters because there's features of interest there that are about that scale and that are not fully resolved at that resolution. So same thing for topography and other flows. It's going to be a gray zone that you encounter as you move to finer and finer resolution for each of these. So one other big takeaway is that being scale aware is helpful while you cross multiple gray zones. So a scale aware closure model like the dynamic reconstruction model seems to help. And that's because you're aware of what resolution you're able to resolve and incorporating that into the closure model. Lateral boundary perturbations may be helpful, like the cell perturbation method. A multi-scale modeling framework where you maybe embed LES grids inside a GCM grid, or you're fine near the wall to generate the appropriate scales. These are ideas that some others are trying. And then finally, another approach is to skip the gray zone entirely. Instead of going from 10 kilometers incrementally down to 100 meters, maybe you just jump all the way to 100 meters by expanding the LES domain. And there's an example here from Schalkwijk et al. In 2015, where they did a GPU simulation, which ran really fast, a large eddy simulation over the entire Netherlands, and at 100 meters, though they didn't really need to nest. They just kind of jumped down to 100 meters. So maybe that's one way to go. But if you skip that gray zone, you'll probably find another gray zone with land use or topography or something else with the closure model along the way. So one last concluding thought is that the dynamic reconstruction model shows some promise in the gray zone. The DRM was originally designed for LES, but it appears to work quite well in the gray zone, what we've seen so far for simulating the convective boundary layer, the stratocumulus boundary layer, and for deep convection. And we think that one of the reasons for this is because the DRM allows for countergradient fluxes and backscatter of energy. So I will show some acknowledgements briefly. This came from various different projects that put together into this story about these multiple gray zones, and I'll leave these here in case anyone wants to look up some of the references. Thank you.
Thank you, Tina. That was fantastic. It's amazing all the problems that come up. So we'll take a minute now for questions. Everybody on the phone, you should be muted, but if you want to unmute yourself and ask a question, feel free, or you can type into the chat box and I can ask it if you're having audio issues or if you'd just rather not have to talk. While you're all figuring that out, I'll go ahead and jump in with one quick question, which is that it was almost philosophical, just that topography as well as atmospheric flows are often highly fractal in nature, right? So there's always a gray zone. Can schemes like the DRM handle almost any resolution, right? Are there like limitations to these where we have to construct semi-artificial boundaries and say, now we resolve convection, now we don't? Or can we develop truly scale-aware parameterizations of sorts that turn off some components as needed or just scale those components appropriately?
Yeah, I think there's going to have to be some kind of hybrid. I mean, we were surprised at how well the DRM did at 1 kilometer resolution. We have not tried much coarser. Maybe we've gone to 2 kilometers or 5 kilometers for a couple test cases. But at some point, there may be other parameterizations that are needed when you have really sharp gradients, like at the cloud top. If you don't have if you're missing some feature completely that maybe you don't know about sometimes, then you'll have to use some kind of parameterization. But I think the scale aware part of it will hold at different scales. Even as you go to very coarse resolutions, there should be some scale awareness in the closure. That's kind of what I'm thinking, but at some resolution, you just won't be able to convect, for example. And so then parameterization is good. Yeah. So I see one question that's come up in the chat, and apologies if I don't pronounce your name correctly. Mustafa says, thank you very much for the excellent presentation. I was wondering is there any plan to include DRM in WRF? Oh, great question. So we have a version in WRF. We have a more complete version in CM1, and Xiaoming Shi, who's at Hong Kong University of Science and Technology now, is working on putting it into WRF, and we have interest from some people. So if you're interested, let us know. It probably needs the usual sort of testing and debugging and all that, but we're very happy to see it be used. So it just needs that like sort of last round of testing before we can put it in the public release.
Cool. I'm sure a lot of people would like to see that. So I was struck by one other thing when you were showing the images of cells developing at different resolutions, which is that the DRM scheme seemed to produce the sort of right scales, but the wrong shapes, right? So the TKE scheme, even though it's now producing these cells that are maybe like 2 or 3 times larger than they should be, it still has maybe better covariance between different properties within that. And is that important? Is that something that's just inevitable in the gray zone and there's no way around it?
So I think you're talking about, let me see if I can find the slide. The convective cases.
So the TKE 1.5 showed just the really large cells.
With this one?
Yeah, something like that, where the bottom right is what you get when you filter the high resolution simulation, but there's something about the spatial pattern in the top where clearly it's the wrong size, but is there something important in that shape?
Yeah, that's a good question. In the Chow et al. Paper, we looked at the higher order statistics to look at what these different sizes, these different structures were doing in terms of the transport in a way. And so there is a difference in, say, what TKE is doing compared to what DRM is doing. And it seems like the DRM reproduces the statistics better of what the finer scale model is doing. So somehow these eddy viscosity models are compensating by creating these large structures, but they're not physical. So I would argue that even though they look like they have the same shape, that they're not actually correct at that resolution.
Yeah. And certainly what you showed, that the cloud cover difference between these, I think, makes a good case for the DRM too.
And part of it is kind of what we see here, that when we do nesting, we often see a lot of large scale structures being fed into the smaller scale domain. And that's because that's what the coarser domain was generating. And they propagate pretty far into the finer resolution simulation. And we spent a lot of time just trying to like break those structures up. So the smaller scale structures seem more in line with what we expect on the finer grid as well. It makes it easier to transition across the scale. So they've also done simulations like this. Jeff Maroka at Livermore has looked at like the different closure options and how they affect development of scales, and others at NCAR have done that too. So it's, definitely want smaller scales to develop faster.
Yeah. Any other questions? Marco says, hello, Tina, thanks for the great presentation. Could you spend 2 more sentences on the main ideas of the cell perturbation model?
Sure. So the cell perturbation method puts perturbations along the inflow boundaries. So the method that's presented in this paper and in others, they use 8 delta X cells and three rows of those. So over the first 24 grid cells at the inflow boundaries, you have 3 sort of checkerboard cells of 8 delta X wide, and you apply perturbations to the potential temperature over a certain height over the boundary layer. And that just helps to trigger turbulence. And you can see it in the energy spectrum. It sort of fills in the finer scales faster. And in this example here, you see much finer structures at this point in the domain than compared to without the CPM. So we've tested it with different setups. A lot of the testing has been done with idealized simulations, and you see a very clear difference when you add CPM and when you don't. And we've been testing it recently over complex terrain to see how important it is to have CPM versus how much the topography can generate on its own, like how many fine scales can just the topography generate. And it seems like the CPM is helpful, but having fine resolution topography may be just as helpful. But that's one of the things that's hard with a standard setup in WRF. As you go to finer resolution, there isn't fine scale topography beyond 1 kilometer resolution that's allowed in WRF. So it's something you have to do manually if you want to include the smaller scale features. But then if you include the smaller scale features in topography, sometimes you run into stability issues because of the terrain falling coordinates. So it depends how fine you're going.
Yeah.
But the idea is just to trigger the very smallest scales. And the reason that the cells are 8 delta x wide instead of 2 delta x is because any 2 delta x perturbations disappear very quickly due to numerical and physical diffusion or turbulent diffusion. Those will disappear. And so that they found in previous studies that the 8 delta x allows enough of a perturbation to sort of persist beyond what the numerical diffusion would take away. And then it allows some scales to get triggered that then are maintained.
Well, and 8 delta x is also about what you're actually resolving, isn't it?
Yeah.
Great. So one last comment, Mustafa says, I'm using TKA 1.5 to simulate MCS over Canadian prairies using 2-kilometer wharf, but now I'm scared after watching your cloud fraction comparison between TKA and DRM. Really interested in using DRM and look forward to it.
Okay, great. Yeah, you can, I'd be happy to get in touch with you. Just email me.
Yeah. Well, thank you once again, Tina. That was a fantastic talk. I really enjoyed it. Everybody else, and Tina for that matter, our next webinar will be in mid-February, aiming for February 20th, where Dave Gotchis will be talking a bit about operational streamflow forecasting in complex terrain. And I want to point out that this has been recorded and we'll have the recording available on the website shortly. Hopefully it will be on YouTube at least this afternoon. I don't know how long it's going to take to get it actually posted on the Mountain Meteorology webinar page, but hopefully fairly soon thereafter. Thank you once again, everyone.
Thank you so much, Ethan. Thanks, everybody.